Okay, we now further refine the root locus by finding the imaginary axis crossing. The importance of J omega axis crossing should be readily apparent. So the J omega crossing by the root locus separates the stable operation and unstable operation for the system. There are two methods to find the J omega axis crossing. The first one is, as you learn in the principal basic instrumentation and control system, which is the root-Hurwitz criterion. And the second method is let the S equal to J omega in the characteristic function, equating both the real part and imaginary part to 0 and solve for omega and k. The values of omega found given the frequencies give the frequencies at which root loci cross the imaginary axis. The value of k corresponding to each frequency gives at the gain at the crossing point. So for finding the J omega axis crossing, I suggest root-Hurwitz criterion. So for this one, we have this closed-loop transfer function. Okay, please remember that for root-Hurwitz criterion, we need to use the closed-loop transfer function system. We take the denominator of the transfer function to construct the root table. So this is the denominator of the closed-loop transfer function. We construct the table based on the highest order. In this case, the highest order is 4, 3, 2, 1 and also 0. So this is even order, odd, even, odd, even. So for even, we just take the gain for the even order 1, 14 and 3. 1, 14 and 3. Okay, this is even, this is odd order. So we take 7, 8 plus k. Okay, 7, 8 plus k and 0. And then we start construct the rest to fill up. The most important is first column. So how to determine this one? 7 multiplied with 14 minus 1 multiplied with 8 plus k divide by 7. For divide by 7, if you do not put it in this equation, that's okay. Just put the denominator and then continue with this one. 90 minus k multiplied with 8 plus k minus 7 multiplied with 21k. Okay, so this is the answer. And if this one is 0, automatically the last row, okay, in this first column is equal to this one. Okay, and then for this one, if we calculate if we want to make sure the system is stable, we have to make sure there's no sign changes in the first column, since it started with positive value, meaning that this one is also larger than 0. This one must be also larger than 0, and this one also must be larger than 0 to keep the first column with positive values and no changes. That's the only way to make sure that the system is stable. No changes in the first column. So all of this equation must be larger than 0. Okay. So we take this one larger equalize to 0. For this one, we equalize to 0 to determine the value of k. In this case, we have k equal to 9.65, and then from this one we move to the row above this one. Okay, we determine from this equation, so we move to the row above this one and construct back the equation where this is this is for even polynomial order. 90 minus k s squared plus 21k. Okay, this one s squared, this one is s with the power of 0. So 90 minus k s squared plus 21k. By substituting this value of k, and then we have this equation, and then we determine the value of s, and which is equal to plus minus j 1.59, meaning that the root locus crosses the j omega axis or the imaginary axis at plus minus j 1.59 at a gain of 9.65. So we conclude that the system is stable for k larger than 0 and k less than 9.65.